But these 4 years have been very busy for Anand actually. He has done a lot of work actually. He wanted to present almost everything. I said it is not possible that you can do all in 35, 40, 45 minutes. So you bring out the main points actually of your experiment. He conducted 5 experiments, different experiments actually. And I do know that there have been PhD theses submitted before, only on one of those experiments. So you can understand the amount of work that he did. So how much time he has to present? 40 minutes? You
including Q&A.
Q&A is after that is 1 hour.
Yeah.
Huh?
No, everything.
Everything. So the presentation is for?
This 20 minutes?
Oh, he can't finish in 20 minutes.
Okay, maybe then, okay.
I think, Anand, you can see here the pressure.
Okay.
Anyway, finish in 30 minutes, right?
Okay.
30 minutes and give some time for questioning. So, Anand, please go ahead.
Okay. Thank you, sir. Good afternoon, everybody. I am Anand Kanatti, research scholar. I am today here to present my doctoral research seminar on genetic architecture of grain, iron and zinc densities and their association with agronomic traits in pearl millet. Iron and zinc deficiencies are serious health problem worldwide. Iron deficiency ranks 9th, zinc deficiency ranks 11th among top 20 risk factor contributing global burden of diseases. India among the countries most affected by deficiency of iron and zinc. About 80% of pregnant women, 52% of non-pregnant women and 74% of children in 6 to 35 months age group suffering from iron deficiency and about 52% of children below 5-year age group suffering from zinc deficiency. Among the various approaches, biofortification of staple crops is most sustainable and cost-effective approach to address this issue, especially rural population and urban poor. The Harvest Plus Challenge program of CJIR has initiated resource mobilization and coordination to support biofortification of several crops, including pearl millet. The focus in pearl millet primarily on iron density and secondarily on zinc density. ICRISAT has already generated some information with respect to genetic variability and genetic control of these micronutrients. The purpose of my research to make further contribution in this direction with these following specific objectives. The first one is to assess genetic effects for grain, iron and zinc densities through line into tester study, to assess tester effect on combining ability of inbred lines for grain, iron and zinc densities, to assess intra-population genetic variation for grain, iron and zinc densities, to assess intra-population variability for combining ability for grain, iron and zinc densities, and to study the correlation of grain, iron and zinc densities with yield and other agronomic trait. Under first objective, we assess gene effects for iron and zinc densities along with other agronomic traits. Here 14B lines are used as a female parent and 14R lines used as a male parent or a testers. And these parents were crossed in line into tester mating design to produce 196 hybrids. Both hybrids and parents were evaluated in side by side blocks for 2 seasons. This is mean square table for line into tester hybrids. Hybrids showed significant variability for all the traits. Lines, tester and line into tester components were significantly contributed for hybrid performance. However, the line into tester interaction component contribution was very low for iron and zinc densities as well as 1000 grain weight and days to flower, and it was very high for grain yield. These components also had significant environmental interaction. The estimates of general combining ability variance was 4 to 5 times higher than that of SCA variance for both micronutrients. This higher GCA variance suggests that these both trait largely under additive genetic control. Similarly, 1000 grain weight and days to flower showed higher proportion of GCA variance, while for grain yield GCA variance was only 50% of that of SCA variance. This larger proportion of SCA variance indicate the grain yield largely under non-additive genetic control. Using information of GCA and SCA variances, we calculated predictability ratio. This predictability ratio indicate if the ratio is near to unity or near to 1, indicate that the trait is largely under additive genetic control. For both iron and zinc density, it shows higher predictability ratio followed by grain weight days to 50% flour. Due to non-additive genetic control, the grain yield shows lower predictability ratio. There were highly significant and high positive correlation between mid-parental value and their hybrid performance. This further confirms that these traits largely under additive genetic control. In other words, when we cross the two parents with high iron and zinc densities, the expected hybrid performance is also high. Hence, to breed for high iron and zinc densities, both the parents should have high iron and zinc densities. Due to this additive genetic control, there was no better parent heterosis observed for these both traits. Similarly, among the agronomic traits also there was highly significant correlation between mid-parental value and hybrid performance, but it was lesser than that of iron and zinc densities, while for grain yield it was lowest. There was highly significant positive correlation between per se performance of the parents and their GCA effect for both iron and zinc densities in both the set of parents. This highly significant high positive correlation between per se performance and their GCA effect suggests that when we select for parents with high iron and zinc densities, it most likely to select for high GCA also. Similar trend was also observed for grain weight and days to flour, while it was very low for grain yield. This suggests that the selection of parents based on per se performance for grain yield is not always select for high GCA effect. And the second objective, we studied the tester effect on combining ability of inbred lines. Here we studied how open pollinated varieties as a tester is going to influence on assessing general combining ability of inbred lines. Here we use two sets of inbred lines, 14B lines and 14R lines. The both inbred were used as a female parents and both were crossed with two open pollinated testers. Here the top cross performance is direct indicator of general combining ability, and both sets of hybrids and parents were evaluated in adjacent blocks for 2 seasons. This is mean square table for B line top crosses. The top crosses showed highly significant variability for all the traits, and B line component of top crosses showed significant variability for iron, zinc and days to flour, while B line into tester component was significant for all the traits except zinc density. This significant B line into tester interaction suggests that there is significant influence of tester on ranking of top crosses. Though the significant B line into tester interaction, but the B line into tester sum of square as that of B line into B line sum of square was very low for both iron and zinc densities. This resulted in highly significant positive correlation between the top crosses. This significant positive correlation between top crosses suggests that both the testers were ranked similarly, both the top crosses, and for grain and for days to flour also showed the similar trend, while for grain 1000 grain weight and grain yield, the contribution of B line into tester interaction component was very high, which resulted non-significant correlation between the top cross performances. This suggests that the selection for GCA for parents were highly tester dependent. Similarly, the correlation between B line performance per se and the top crosses were highly significant for both iron and zinc densities with tester 1 and tester 2, and it was further improved when we use the average of both the tester. This significant correlation between perceived performance and the top cost suggests that there is a positive correlation between perceived performance and their GCA effect. And this trend was also observed in line into tester mating design also. The similar trend was also observed for days to flower and 1000 grain weight, while it was non-significant for grain yield. This indicates that the GCA performance is not significantly correlated with perceived performance of inbred parents. Similarly, R-line top crosses also showed significant variability for all the traits, while R-line component of top crosses were significant for all the traits except grain yield, and R-line into tester component was significant for all the traits. Though the significant R-line into tester interaction component, the proportion of contribution of R-line sum of square as that of R-line sum of square was very low for both iron and zinc density, which resulted in highly significant correlation between the top crosses. The similar trend was also observed for days to flower, while for grain weight and grain yield, the line R-line into tester sum of square was very low compared to that of B-line into tester interaction, which resulted highly significant positive correlation for these traits also. Similarly, the correlation between performance of R-lines and their top crosses were highly significant for both iron and zinc densities. This suggests that there is significant correlation between perceived performance and their GCA effect, and either of the tester is equally effective for selection for high GCA effect. Similar trend was also observed for days to flower and 1000 grain weight, while it was non-significant for grain yield. Under objective 3, we assessed intra-population genetic variances in 2 open pollinated varieties. These 2 open pollinated varieties were identified for high iron and zinc densities in earlier studied. The progenies were developed using North Carolina mating design 1. In this mating design, the randomly selected male were crossed with the 4 randomly selected female parent. Once female parent crossed with particular male parent, it should not be involved in any other crosses. Like that, 40 random males were selected from each population and were crossed with 40 different females, and total 160 progenies were developed in each base population. Further, these 160 progenies were subgrouped into 10 sets, each set representing 16 hybrids. These 16 hybrids belongs to the 4 male group, and each set was randomized separately, and all the sets were evaluated in compact blocks to reduce the soil heterogeneity. And this mating design represents the highest variability of the base population, because due to this mating design, the different males and different female combination mating design. The genetic variances from this North Carolina mating design estimated if the male components showed a significant variability for traits, it suggests that there was significant variability among the half sibs, which will give direct estimate of additive variance. While females in males in set component were significant, means it suggests that there is significant variability among the female parents, which will give the total genetic variance, which include both additive and dominance variance. This is mean square table for ICTP 8230 population. Here males in set component was significant for all the traits, suggests that the significant variability observed for additive genetic variance for all the traits, while males in sets into environmental component was non-significant for all the traits, suggests that there were not significant influence of environment on estimate of additive genetic variance. Similarly, in ICME 221 population also, the male component was significant for all the traits, it was non-significant for days to flower, while males in set environmental component was non-significant for all the traits except days to flower. These estimates of additive variance were 4 to 5 times higher than that of dominance variance in both ICTP as well as in ICME. This confirms that these traits were largely under additive genetic control. This trend was also we saw in line into tester mating design also. While 1000 grain weight showed higher proportion of dominance variance, in both ICTP as well as in ICMA 221 population, while days to flower showed higher proportion of additive variance in both the population. The estimate of dominant into environmental component variance was very high for all the traits in both the population, and this dominance into environmental variance is higher than that of dominance variance estimate for both iron and zinc densities in both the population. This suggests that the estimate of dominance variance is highly compounded with the environmental interaction component for both iron and zinc densities. Under fourth objective, we assessed intra-population variability for combining ability in open pollinated varieties. These two populations were identified for high iron and zinc densities. The two open pollinated testers were used, and in each population 60 randomly selected H0 plants were used. Now, each plant was crossed with both the tester, and these top crosses were evaluated for 2 seasons. There was significant variability observed among the top crosses for all the traits, while plant component of top crosses were significant for all the traits, and plant into tester interaction component was significant for all the traits except zinc density. Similarly, in ICMA 221 also, top crosses showed significant variability for all the traits, while plant component was significant for all the traits except days to flower, and plant into tester interaction component was non-significant for iron and zinc densities and significant for grain weight and days to flower. Look at here, the plant into tester interaction sum of square as that of plant sum of square was very high for iron and zinc densities. This resulted the low correlation between the top crosses of both the tester. This suggests that the selection of early generation material for high GCA effect using OPE tester is not much effective. In other words, the GCA of H0 plants were highly tester dependent. While in ICMA 221 population, the plant into tester sum of square was only 30% for iron and 20% for zinc, which resulted highly significant correlation between the top crosses. Here the correlation was much higher than that of ICTP A203, but this correlation was not that much higher than what we observed in advanced inbred lines in inbred top cross trial. This suggests that the testers were not consistent in ranking of S0 plant top crosses in both the population. This study required further investigation using how the tester were influencing on early generation genetic material. This large variation might arise due to the large variability within the population of within the plants of S0 plants. The similar trend was also observed for both grain weight, days to flower. Here the plant into tester sum of square was very low for days to flower and 1000 grain weight, which resulted highly significant correlation, while it was very high in ICMA 221 resulted low correlation. Here also the same trend what we saw in the iron and zinc densities. Under objective 5, we study the correlation of iron and zinc densities with grain yield and other agronomic traits. We used here 2 sets of hybrid, set A with 32 hybrids, set B with 28 hybrids, and both the sets were evaluated for 3 environment, including ICRISAT potential as a common location. There was highly significant variability among the traits in both set A and set B, and also there was highly significant H into E interaction for iron, zinc, grain weight and grain yield. This highly significant environmental interaction for grain yield, which varied due to this, the grain yield was varied from 2 to 4-fold in individual environment. Among the micronutrients, the zinc density showed higher variability in individual environments. Similarly, days to flower, plant height, panicle length and effective tillers were also showed significant variability among the hybrids in set A and set B, and H into E interaction also significant for all the traits. This is correlation averaged across the environment in set A hybrids. Here iron and zinc density shows highly significant correlation, and iron and zinc densities were non-significantly correlated with 1000 grain weight, while iron showed significant and moderate negative correlation with grain yield, while zinc density showed non-significant correlation with grain yield, and also iron showed non-significant significant correlation with days to flower, and zinc having non-significant correlation with days to flower and as well as other agronomic traits. In other hand, the grain yield showed significant positive correlation with days to flower, plant height and panicle length. The same trend was also observed in set B hybrids. There was significant positive correlation between grain, iron and zinc density. This suggests that the both micronutrients can be enhanced simultaneously. And here also iron zinc density was non-significant while zinc density was positively significant. From both sets of hybrid, we can say that the zinc density was showing either significant positive or non-significant correlation, says that high iron and zinc densities can be combined with large seeded genetic background, and iron density showed significant negative correlation while zinc density was non-significant correlation with grain yield. From both the set, the negative correlation between grain yield and micronutrients varied from moderate to low in individual environment, but it is not always significant. This negative correlation might arise due to the genetics of trait. The grain, iron and zinc densities were additively controlled while grain yield was dominance control, non-additive control. Due to this additive control of grain, iron and zinc density, both the parents should have high iron and zinc densities, and both the parents makes the diversity between both the parents were reduced. This reduced diversity between the parents might have caused the heterosis for grain yield, and it might have resulted negative correlation between grain yield and micronutrients. And second cause might be due to the source of iron and zinc densities. Whatever the parental combination we used for these both set of hybrids, the most of them were derived from only single source, that is Iniadi germplasm, which is the only source still today used for development of these high iron and zinc density inbred lines. Due to this single source, this might have reduced the diversity between the parents, which might have caused reduced heterosis for grain yield, and it might be also due to the grain yield is negatively correlated with both the micronutrients while it's positively correlated with days to flower, plant height and panicle length. It is not much clarity was observed how much this positive correlation with the grain yield influencing on the negative correlation between the grain yield and iron and zinc densities, and it might also arise due to the natural relationship between these traits. The principal component analysis, which take all the traits considered together and which will group all the traits according to their relationship. Both iron and zinc were grouped together, means this is positively related, while grain yield, panicle length, days to flower and plant height were grouped together due to their positive relation among themselves, while the grain weight is either positively or non-significantly correlated with both the groups of traits. The similar trend was also observed in set B. The grain, iron and zinc densities were positively related, while grain yield, panicle length, days to flower were positively related, and 1000 grain weight was either positively or non-significantly related with both the group. In line into tester study also, the inbred line showed non-significant correlation with grain yield as well as 1000 grain weight, while both the micronutrients were negatively correlated, but the lower in magnitude in hybrids, and these micronutrients were positively related with 1000 grain weight. In topcross study, the correlations between the micronutrients and agronomic traits were non-significant for in all the combinations, while R line into ICMR 312 showed positive correlation with the grain yield. From this correlation study suggests that there is possibility to breed high iron and zinc density hybrids with high grain yield. By conventional breeding method, we should have to maintain the larger breeding population than that of yield alone, which will give the opportunity to get the combinations of high iron and zinc densities as well as high grain yield. The second thing, through marker assisted selection. Using the marker assisted selection, the genomic region responsible for high iron and zinc density should be incorporated into both the parent, and both the parents should be maintained for high diversity for grain yield, which can give the opportunity to breed hybrids for high iron and zinc density as well as high grain yield. The other possibility is we can go for alternative source for iron and zinc density to maintain the diversity between the parents. From all these studies, I can conclude my seminar with these points. There was much similarity in genetics of both iron and zinc densities, which were highly significant and positively correlated, and the concentration of both can be enhanced simultaneously. The predominance of additive genetic variants observed in both inbred lines and populations. This suggests that recurrent selection for intra-population improvement and open pollinated variety development is likely to be highly effective. Both the parents should have high micronutrients to breed micronutrient dense hybrids. Highly significant association between parental performance per se and their GC effects suggests selection based on performance per se would be highly effective in selecting for GCA. In inbred lines, hybrids and topcross showed significant positive or non-significant association between micronutrients and 1000 grain weight suggests that possibility of simultaneous improvement of both micronutrients in large seeded genetic background. Low to moderate negative correlation between micronutrients in advanced hybrids, though it was not significant in all the cases, and the low negative correlation in line into tester trial and no correlation in topcross trial indicate that iron and zinc density can be combined with grain yield. Very little tester effect was observed on ranking of inbred lines for GCA for both iron and zinc densities. And I would like to acknowledge those who are helped for my successful completion of this my doctoral degree program. First, I would like to thank Pearl Millet breeding team, especially Dr. K. N. Rice sir. He is a co-chairperson for my advisory committee. He guided and he in all the stages he encouraged to do my research, and I feel very lucky to work with him. And also I would like to thank Dr. M. Govindraj, Dr. S. K. Gupta sir, and Mr. A. S. Rao and V. Iswar Rao. I would like to thank my advisory committee chairman Dr. K. Radhika for her constant guidelines and encouragement during my tenure of this PhD program. And I would like to thank P. Janila Madam and V. Padma. These are my advisory committee members. I would like to thank Charles Renard Analytical Laboratory, ICRISAT, especially Dr. K. R. Sherawat sir and Mr. Srinivasu for timely analyzing micronutrients. I would like to thank Department of Genetics and Plant Breeding Angro providing this opportunity to work in ICRISAT. I would like to thank ICR New Delhi providing senior research fellowship for 3 years and Harvest Plus Challenge program for funding for this research, and also I took fellowship from this Harvest Plus program in my 4th year degree program. I would like to thank Learning System Unit ICRISAT, Library Information Services ICRISAT, and Housing and Food Services. Thank you one and all.
Thank you, Anand. I think this was a very fast presentation covering a lot of ground. And he started 6 minutes after 2 o'clock, so you finished just in time. Now the presentation is open for questions, clarifications.
In objective 2, how your two OPVs, that is RAJ 171 and ICMR 312, with respect to the iron and zinc content in comparison with the B and R line.
Open pollinated testers, iron and zinc content.
Yeah.
Testers?
Yes.
Okay. ICMR 31 having higher iron zinc density than that of Raj 171.
So how about Raj?
Raj
What's the
171
actual
having
range of content?
around 45 ppm in Raj 171, around 50 to 55 ppm in ICMR 312. ICMR 312 having higher iron and zinc density.
So what was the range in B and R lines?
B and R line, it ranging from 40 to 90 ppm. We selected all the range, low, medium and high.
So your Raj 17 acts as of low type or medium type, you consider?
Not we call low, it is medium types.
Medium.
Yes, sir.
So the other one is high type?
High. But initially we not selected specifically with high or low, we selected only as a open pollinated tester.
Why did you use your North Carolina one when you have already used lines to tester and then lines with OPV? What is the specific advantage of North Carolina one in your mind?
We planned this one to know what is the gene action in original population itself. Because when we get the inbred lines from such type of random mating populations, which may change the relationship, whether it is consistent, because in all the traits we see that someone will report additive control, someone will report non-additive, someone will report additive and non-additive control. Whether this trend in inbred lines, whatever we saw, whether it also found in open pollinated populations.
Why I am saying, because you estimated 4.4 A plus variance conditions.
Okay, 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 sir.
That you can do by generating any food source. Because if you see the covariance of food source is half A plus quarter D. So that also you can estimate. So it's nothing but generating food source. And
Yes.
information you can also get from managed tester. Because managed tester also generates full source and half source. So that information, and if you believe that generating this information from OPV and generating from managed tester, the lines are coming in and our lines are different, I don't think so.
I think that will be a little high question for Anand. No, what you are saying is true actually. But when you do line into tester analysis, your lines and the testers, they come from very different backgrounds actually, from very different crosses. What we wanted to know, precisely I think the background is like this. We developed a biofortified high iron variety out of ICTP 8203. And in one cycle we made a gain of about 9%. So when most of the variability is of the additive type, you expect, like he is concluding, intra-population improvement is likely to be effective, right? But let me tell you, that was a very messy way. We did not know much about how to screen and what type of material, whether we should evaluate the self-seed, the SIP seed or OP seed. That is how the Athanasakti, the high iron version, was developed. When we came to know that, I think it is a good idea to use open pollinated seed rather than self-seed, then we took another round actually. Dr. Govindraj has completed that work actually. So what we wanted to know was that if the intra-population variability is largely of the additive type, you are going to be highly effective actually in improving it further if in case there is variability. But we wanted to know whether within the population the variability is predominantly of additive type or not. So that was the reason for that he took those two populations. So both have got high iron actually, ICMB 221 and ICTP 8203. And the result that he found was the same as by line into test analysis. So what you were saying, he got no new information actually. But he showed that within the population also there is substantial variability and it is largely of the additive type. That was one. So within the population you cannot do line into tester actually, but you can do full saves.
You can do this. In fact, if you see over here, these estimates,
Yeah.
to me, both estimates of additive genetic variance as well as variance due to dominance deviations are highly inflated, because unless you take out the epistatic component of variation,
That's correct.
which we cannot do over here, in the presence of epistatic variation, which we have not taken off,
Yeah.
these are of very highly inflated, or to an unknown extent they are. And that's why any of studies you do, you will also conclude, I will also conclude, third person will also conclude, that mostly it was additive, dominance was also present there. Because we are not taking out it compartment-wise, the basic factor, which is much more important, say whether additive into additive or additive into dominance deviations. And this additive, if you further partition by it within the same population, you will find that real additive, variance due to additive genetic effects, would be much lower than additive into additive component. And in groundnut we showed really, I think it was long back, 10, 12 years back paper, that additive component was much less than additive into additive. That epistatic variations were much more higher. And the moment they are present there, your all estimates, unless you take it off, are biased to a very unknown extent. And that's why you will never find any difference of results. In fact, if I ask you one simple question, not to you, to anybody, even to me, if I do the same thing, did I find any unexpected result?
Yes, sir.
All of these results are expected. I have done the same thing, my results also become expected, unless the basic component is taken off.
Yeah, that is true. I mean, this model does assume that there is no epistasis, right?
Yes.
But in fact there is, right?
Yes, sir.
And this way we cannot estimate it. So we don't know in a relative term which one is more influenced by epistasis, the additive or the dominance. So you have to assume actually, okay, the epistatic contribution proportionately is same for dominance and for additive, but overall you find the additive component is more. The idea here was, let me tell you how does it translate it. By the time he was doing this study, Govindraj did start the selection experiment within each one of those. And surprisingly, he finds very good response actually about, I don't know, about 12 to 13% in ICTP 8203 and about 18% in 221. 221, why we are getting higher is because it is slightly broad-based population. So there is more variation. So you find larger response. ICTP is slightly narrow, much more narrow, based only on 6 lines actually. So you get less response. But in both, in open pollinated varieties for a character, 12%, 17%, 18% response in one cycle is very high.
I'm interested in asking how you chose some of your parental lines. You know, you had 28 parental lines right at the beginning. I have no idea about pearl millet. I don't know anything about the germplasm or anything. So how did you select those 28 lines?
These 28 parental lines were selected for all the diversity for iron and zinc density, both low, medium and high. All the combinations parental lines were selected in line into tester meeting design.
How do you see the additive nature as a constraint for development of biofortified hybrids?
Yes, sir. If additive genetic control means we can't get the better parent heterosis for that particular trait. Both the parents should have high iron and zinc density, and the expected hybrid performance is in between the average of both the parents. In hybrid development, it is rarely constant, and it will reducing the diversity between the parents, and it will reducing grain yield until we get the diversity alternative source for grain iron and zinc densities. There is not much possibility to get high yield as well as high iron and zinc densities. There is a consent, but there is a possibility also to breed high iron and zinc densities.
One more. I'm talking about genetic loci controlling these traits. Do you or does anybody have any idea how many loci might be involved, important loci in regulating these zinc and iron content? I mean, is there just one, or does anybody know, or?
Yes, in earlier studies they reported more than 4 QTLs like that. I read in article, but I don't know exactly. I read about around 4 QTLs, 5 QTLs were controlled by these states.
Very simple. She asked, is it one or more than one? So you say it is not one, surely,
Okay,
right?
yes.
It has multigenic control actually, but we think by going through the literature in the other crops that there are major genes actually involved. The question will be different whether we are going to follow that major gene approach actually, or we are going to follow the genomic approach actually in the future. That we will have to see. But one thing is very clear, that if we want to accelerate the hybrid breeding for high iron and zinc, the genomic tools are going to be very, very helpful actually. Because the source is so far only one type, Iniadi germplasm. Although there may be variability within Iniadi that we don't know, we are still investigating. So if you use the same Iniadi source on both male and female side, you have to breed for high iron, right? So you have to incorporate the same genes on both sides. And while doing that, maybe along with those genes you are bringing the other genomic regions also, which are similar and which might be related with the grain yield heterosis. So the diversity for the other traits goes down, and as a result, the heterosis for the grain yield goes down. So we have on several occasions made very strong proposal actually for genomics approach to develop biofortified hybrid high grain yield. Let us see how far we go.
I'm no breeder, so I really don't know whether my question will have merit, but one of your recommendations is that iron and zinc, you can address it both together. So are there instances where you can only address one, or why is it that you can address both in just one go?
Why we want to both?
No. So your recommendation is that iron and zinc can be addressed together?
Yes.
In just one maybe study or research. But are there instances where you can only address one nutrient, like for instance maybe not together with iron and zinc, like boron maybe, or I don't know. That's why I said I don't know if my question is in place, or why is it that you can do both iron and zinc together? Are they very much related, or?
Yes, they are highly positively correlated.
Okay. All right. Oh, okay.
Yeah, your question is why? Why?
Yeah.
There could be several
Why we want to?
Why they are positively correlated?
Yeah, yeah.
Why they are positively correlated?
Yes.
it might be due to the both the traits were controlled by the same genes. Same genes were controlled by both the traits, or both the traits controlling the genes were highly linked together. They were linked gene, or the similar gene are controlling the both the traits. There is two possibility.
There is evidence in other crops actually, a very limited information in pearl millet, that though there are 4 genes or 5 genes or 5 loci, I will call, not genes, some of them co-segregate actually. They are reasonably linked together. So that might be one of the reasons that you get positive correlation. But since all of them are, all for iron and all for zinc are not linked together, so you don't get correlation of, let us say, 1. It varies actually. So some co-segregation because of the, whether you got slightly tight linkage between the iron and zinc loci is there. But whether there are loci common loci both for iron and zinc, right? That is interesting to find out.
Can I make a general comment? Yeah, I think there is an aspect related to better agronomy also. So it is not really, even if you have the best gene, it will not get expressed unless there is better agronomy. In fact, there is a large body of literature gathering whereby improved nutrition, balanced nutrition of crops, you can really enhance and attain the potential of improved cultivars for iron and zinc. Then there are several aspects. In fact, if you have high phosphorus in the soil, that will really counteract uptake and metabolism of zinc. If zinc is just marginal. Similarly, zinc and iron also could be really antagonistic, particularly if sulfur and iron also. So there is so many interactions, but in case you just have everything in a balanced manner, I think perhaps you will get best results expressed of those cultivars. Thank you.
Any other question? None?
Let's go from the scholars.
Okay, let us thank the speaker again for the good job done.
So, thank you, Anand. So before we go for tea, let's have a little ceremony for his certificate of participation. Okay? Okay. So may I call on Anand and Dr. Ken Roy?
You can show him.
Sir?
You can show him.
Sure, of course. So this is your certificate of participation. Above there you have the logo of ICRISAT. Is awarded to Anand upon successful completion of research scholarship on genetic architecture of grain, iron, and zinc densities, and their association with agronomic traits in pearl millet, Pennisetum, glaucum, blah blah blah, from 11 April 2011 to 14 August 2014 at ICRISAT, Patancheru, Telangana, India, signed by no other our Director General, William D. Dar. So, Anand, please come. Here? So let's go inside so that this chair is on. I think it's okay. Come, Anand. So you stay in the middle. Okay, so stop. Right.